Okay, probability review. So, are you looking for me to just go literally from the very, very beginning of probability and then go as far as we can?
Does like this have like does it have conditional and stuff? Because I know a little bit of probability, obviously, from year 10.
Yeah, I think the beginning of what you said cut out. Were you just looking to start a conditional probability?
No, like I said, I know like conditional probability, independent events, mutually exclusive. Like I know a bit of like the starter up stuff.
Yeah, okay. Well, if you got it to mutually exclusive, then you've finished all the fundamentals. The next thing would be to go on to counting method stuff.
Yeah.
Yep.
Then I guess yeah, I wouldn't mind doing that. I
Let's
did
do
a
it.
little bit of permutations and combinations with Ksenia, but then
Hmm.
yeah.
Yeah, cool. So I guess what I'll do is I'll introduce some concepts, and if at any point there's things you want to look at in the actual textbook itself, just let me know, and we'll deviate towards doing that so you can get some actual reps in.
Yeah.
Cool. Okay, so fundamentals of counting methods, starting with addition and multiplication principles. These are things we kind of know implicitly. Like, for instance, the addition principle just means if you're choosing from a whole array of choices, then the choices add together. Like, for instance, if you're choosing your main meal, you might have pastas, you might have pizzas. Doesn't really matter what they're grouped as, you're still just choosing one main meal. They all belong to the same overall category of main meal. So you add all those selections together.
Yeah.
Multiplication, however, comes into play whenever you're doing things in a sequence. Like, for instance, if you were to do an entree, then a main, then a dessert, suddenly you're doing things in a sequence. The number of choices that you can now make would be multiplicative for each stage. The example I give here would be something to the effect of you can choose to either walk or drive to go to the gym, and then once you're there, once you actually choose your selection of exercise, you could do potentially cardio or weights. If you want to figure out all the combinations in that particular scenario, you do multiplication, more or less. You're doing a tree diagram. All right, you either drive or walk, and then once you've walked or drove, you've now got two further options to choose from. As far as how it can apply to probability, it's always going to be based around figuring out either the total number of combinations that exist in the scenario, capital N, or the number of combinations that are desirable for a particular probability, in this case, capital X. As a quick example, let's say we're choosing 6 subjects for Year 11, and there's 3 that have already been chosen. Here's a list of options for selection. What is the total number of possible selections? Well, you're just adding literally all this up. Doesn't matter that this belongs to that group. You just, you got 3 here, you got 2 here, 5 and 3. You're just adding all that up. Oh, wait, sorry, this is done in sequence. My bad. We're not choosing 1, we're choosing 3 more because we've got 6 in total. Yeah, so if we're trying to figure out for literally all possible choices to fill out that entire subject selection, since there were 3 left, you do a multiplicative on that. Probably selecting a science, you're basically now just looking within only the sciences, and more or less it's just there to help you calculate either desirable or total combinations for the scenario. Cool?
Yeah.
Okay. Arrangements and permutations. So, one of the things that is often asked is to calculate the number of ways in which a certain number of objects, people, whatevers can be created or selected. It's easy enough to do when you have very little sample size. You can literally just go through and go, oh yeah, I've got red, green, and blue. I could arrange those in those particular orders. Anything bigger than that, you're going to start to run into issues there. The way I've found is quite helpful to think about things is to think about how many positions do I have and how many choices for those positions do I have. Like, for instance, I've got 10 objects and I've got 10 spots to put them, right? If I'm just trying to arrange them in some sort of row. Like, let's say I'm trying to fill out a bookshelf, right? I've got 10 spots on the bookshelf, 10 books. For that first position, when I make my first choice, I've got 10 possible options to put in that position. As of that point, I've now chosen one, so the next slot now has 9 remaining choices for it. Rinse repeat until you get to the end of the array. And because you've done these in a sequence, you've chosen position 1, then position 2, 3, 4, 5, so on and so forth, this is now multiplicative across the board. So this is an application of the multiplication principle.
Yeah.
Uh, this is factorial, right? When you have the same number of positions for a thing as you do objects for that thing, um, it arranges itself in this particular way where you have a decrement of each number. This would be considered 10 factorial. For another example, 5 factorial will just be starting at 5 and decrementing down to 1. Whatever the number is, you start at that and decrement all the way down to 1.
Yeah.
Permutations is basically the exact same thing. In fact, it's literally the same thing if you've just gone based off how I've described it. It's just how many positions do I have, and how many objects for those positions do I have. Let's say the shelf only has 3 spots left on it. That's cool. 10 by 9 by 8, we're just truncating that, cutting it off early. This is referred to as arrangements or permutations. You'll notice the permutations equation. You can actually calculate this via equation. It's probably easier just to do this, but this also does exist. You're still fundamentally doing the same thing. To calculate combinations in a permutations manner, you want to do n factorial over n take r, where n is the number of options or objects that you have, and r is the number that of positions you have, or the number that you're selecting, effectively.
Yeah.
And when you do it, you'll find out that the math, basically what you're doing is creating the exact same thing, where instead of having 10 by 9 by 8 all the way down to 1, because from that point onwards everything cancels down, you get left with 10 by 9 by 8 once again. These are used when the order is considered important, right? Like, for instance, if for whatever reason you're choosing flavors for your ice cream, and you really want to make sure that first scoop is either your favorite or second favorite, then maybe the order in which you select those scoops is actually going to matter. And so what you'll end up with is duplicate combinations, or at least what appear to be duplicates. Chocolate vanilla, vanilla chocolate. Those are considered distinct and unique combinations in this scenario when you're calculating via permutations. The next thing we look at is selections, which basically eliminates all of these so-called duplicates. As far as applying it to probability, it's the same thing always. Right? All these counting methods that we're looking at are effectively there to help us calculate either the total number of possible outcomes or the number of desirable outcomes. There's a whole bunch of examples here. Like, for instance, some of the wording can be a bit strange around them. This one's probably one of the ones worth identifying, which is, what is the probability that the 2 rear seats remain empty? This is where you want to make sure you want to have a sort of good approach to addressing these kinds of questions. And yes, one of the things you want to do is probably start using this positions metaphor for, like, how many positions do I have? How many choices do I have for those positions? The other thing that I like to do is also think of addressing the restriction first, and then backfilling later. At least in particular when you're calculating your X, the number of desirable outcomes. Calculating total is pretty much always the same thing. There's not usually too many complications around that. You're basically just looking for, okay, ignore the fact that this is saying 2 seats remain empty. I just want to figure out how many possible selections do I have for that passenger. There's 3 in total, and then 10 seats for them, so you just decrement down. That's chill. However, in this scenario, because the 2 rear seats remain empty, the easiest way that I could think of to simplify that would just be to say, hey, we don't have 10 seats anymore. We've only got 8. And so that is upfront addressing that restriction and then backfilling, right? We knock off the 2 of the 10 and then fill in the remaining afterwards.
Yeah.
That gives us our X, and then it's just division. Similar here, we're now ensuring that they're filled rather than anything else. You got to get a bit creative with it. Um, you'll notice that the scenario hasn't changed too much, so we can reuse our capital N. However, when it comes to calculating capital X, we're now trying to fill those seats. And so to address that restriction first, we're going to say, okay, to fill those seats, because we now have less seats than people, we're now going to start assigning people to seats rather than seats to people. You pretty much always want to have the position to be the number of positions to be less than the number of things you have, or I suppose I should say less than or equal to. Which is why we're changing from assigning seats to people rather than people to seats.
Yeah.
So to fill those in, you got 3 people, and yeah, so you got your 3 then 2, because you got 3 people that could go in that first spot, 2 people that could go in that next spot, and once you've filled in those 2 rear seats, that last person has wherever else they want to sit. So it can be a bit hidden just by looking at that, what's going on. That's why you typically just start with the restriction first and then backfill later.
Yeah.
That's arrangements and permutations. Lastly is selection stuff. So literally all we're doing in there is chucking an additional division by r factorial. I'm sure there's some strong math reason for why that works. Didn't really look into it. All I know is that you're basically excluding all those duplicate combinations. That's usually referred to as NCR. Sometimes you'll see this sort of array looking thing.
Yeah, I saw that with Ksenia. She likes to use that thing.
Oh, she does, yeah. It's probably the most succinct way to do it. Like, this is big, and this is kind of weird because you've got to use 3 separate levels. This is probably the nicest way. Yeah. Cool. So typically you'll use this when you, yes, want to exclude those duplicates, but potentially another way of thinking about it would be to say the order in which you're arranging a thing is relevant. And usually this is when you have groups of people. If you have named people making a team of some sort, a team of Dan and Kim is the same as a team of Kim and Dan. As long as you don't care about like the positions that they're playing in that team. Typically speaking, you wouldn't see people referring to, even within, if you did have different positions within that team, you still wouldn't consider it a different team just because someone's playing a different position than they would otherwise. And so for that reason, you tend to default to selections. One of the other things that tends to come into play here is you're still doing a multiplication principle when you're working with these team-based scenarios. Like, for instance, we want to figure out how many teams you can make from 4 people. Yeah, from 4 people. Well, sorry, how many unique... He's gone! He's crashed. Alright. We shall pause. Hey,
Oh,
hey.
I'm sorry about that.
No, you're good. You're good. When did you drop off?
This time I just decided to, take things into my own hands as soon as it froze.
Yes, yes, okay. Um, how? Yeah, okay. I was starting to give the example there. Have you heard that yet?
No.
Okay, cool. So in the example here, we have 4 people, 2 teams to make. We want to figure out how many ways we could create those teams, unique teams. And so we're going to do because you're trying to create 2 separate teams, you're now doing basically creating one team and then the other team. That is a thing done in sequence. It is a multiplication principle. Now, each of those positions, because we're creating unique teams where the order is irrelevant, we're using the selections equation to calculate each of those number of combinations.
Yeah, because then you're saying wherever the order matters, you want to use permutations, otherwise you use selections.
Yeah, yeah, effectively. Um, that's how I've tended to think about things. There's technically other ways of doing it. This is just sort of the thing that's been most widely applicable in like the vast majority of scenarios. Because there's going to be things that break. There's going to be things you come across that break this a little bit, and you're going to have to be a bit creative with how you handle it. Um, but this will help you in the vast majority of circumstances. But yeah, just be sure when you do these kinds of things, make sure to figure out whether or not you need to decrement n. Like, for instance, the four that we were using here was just, hey, we have four total people. And so to create the first team, we have four and we're choosing two. We've already chosen two. We've now got only two left to select from. Versus what's probably a bit more common in the book will be they'll have like 6 boys, 4 girls, figure out how many teams will have, I don't know, greater than 2 girls or something like that. There's very clear, distinct groups there with different n sizes that you can use. It's not usual that they'll have a big conglomerate of people and then say calculate based off of that. Although you will be using the addition of those two things for your total, capital N, when it comes to doing capital X stuff, which is more or less what's happening here. Um, those subgroups will be a bit more obvious.
And just to confirm, right, 0 factorial is 1?
0 factorial is 1, yeah, by
Okay.
by definition and nothing else.
Okay.
No other reason for it other than it's convenient, which happens a couple of times in math, which is a bit strange to think about, but yeah. And so yeah, this gives me an overall thing that you can use to now start handling most sorts of questions. Um, multiplication principle you can pretty much use for pretty much anything other than um, order being unimportant. Because even with permutations is fundamentally just chopping multiplication principle off earlier. And so rather than thinking about 3 separate things to do, you're probably better off thinking about only really 2 main things. I don't really see too much advantage of being able to use permutations versus multiplication principle. But anyway, so if you can repeat choices in the sample space, like for instance, when you're creating like X number of digit numbers from 0 to 9, if you can reuse that digit 9999, then none of the other counting methods are going to work because they all, from multiplication principle onwards, they're all implying that the number of choices decrementing for each selection. That's why you have a 10, then 9, and 8, rather than 10, 10, 10. So if you can repeat things within the group of objects that you have, if you have infinite of each possible option, then your only bet there is going to be multiplication principle. The remaining two can be used if you can't reuse those options, and as you said before, the order is the main thing. So whether AB is different to the word BA, or whether AB is the same as BA. That's when you'll use either permutations or combinations, or more realistically, just multiplication principle up here. Here's that example, right? So the idea here is that we can reuse digits. And so if you want to figure out, what is this one here? 4-digit numbers, just keep in mind there's sometimes implied conditions in here. A 4-digit number. The implied condition here is that, well, you're not going to start with a 0. No one ever says 0, 100. It's just 100. And so making sure to be a bit perceptive of these. But more realistically, you'll just sort of do a lot of questions and then just by default understand, oh, right, cool, it's this thing again. I've got to make sure I don't put a 0 in the leading spot. Got it. It's those kinds of things where you'll fail the first one and then never again because you've noticed the issue with it.
Yeah.
Um, Here's the qualifier without repeated numbers, so you can then use your permutations equation, or again, just working with multiplication principle. Um, and once again, even though this does look a bit weird, the reason why is because we're addressing the restriction up front. So you've got 9 possible options because you can't use the 0 at the start, and then again 9 because yes, we've got rid of the 0, but we've yes, we reintroduced the 0 in this one, but we decremented whatever we used in the previous selection. That's why you have 9, 9 in that one. And here's the basic teams example: 8 boys, 5 girls. How many teams are possible? Well, it's a team of 3 boys and 3 girls. So basically, of each of these subgroups, we are selecting 3 from them. It's teams, so we're going to use selections. There's 8 boys, we're choosing 3. There's 5 girls, we're choosing 3. And because when you select people, you do it in a sequence, it is a multiplication principle. If you then wanted to find the probability of this happening, you're then just going to divide by total, where you would add up the 8 and 5 and use that as your capital N, and you would add the 3 and 3 to 6, and that becomes your R for the bottom. Yeah, that's pretty much it. This is more or less just a repeat of that. First thing I'll do is typically find my total number of combinations, since that's the thing that has the least amount of crap around it to sort through. And you can use your counting methods to help with that. Then from there, the top X, that you can usually use all of these to help out there, but again, sometimes there are some implied or explicit conditions to worry about. Like, for instance, this is not, well, sorry, this is not straight arrangements, right? You have to do a slight qualifier around it. And then, well, obviously, once you have the 2, you just do a division. That's chill. Do you want to have a practice of these or keep going with concepts?
Yeah, let's have some practice, I guess.
Okay. Any one of them in particular, or just straight to like quick fires?
Yeah, maybe like a like some chapter
Yeah,
review questions
chapter
of
3.
them.
Sure. All right. Let me pull up the unit 1 and 2 because that's what this is from. Counting methods, chapter 10, 382. Yeah, fast. Okay. The tech free ones. The decent way to start. Do tech free, tech active, multis. I reckon probably the extendeds would be good if you're. Do you reckon you could jump straight into extended response?
I'll try my best.
Let's find out. If you're having a bit of issues with it, we'll jump back to the tech free stuff.
Yeah, no worries. Question 1?
Yeah, we'll just go from the top until you're satisfied with your abilities.
96.
96. Okay, so is that just 4 by 6 by 4? Yeah, okay. Sweet. Yeah, I'm just pulling up the answers in the background. Yep.
Okay, I'll do 1B real quick.
Yep.
120.
Just give me a sec. Yes, 120. That's it. Couple ways you could handle that with the oh, whoops. Where'd it go? There it is. With the omitting, did you just make that its own choice?
Yeah,
Yeah, that's
just trying to visualize it as like a tree diagram, I guess.
yeah. So a lot of these are going to be helpful by tree diagram. Just thinking, okay, cool. It's actually a 4th choice now, or whatever the number was there to now omit. Because dessert was so it's a 5th choice then. Cool. Part C, very similar thing, omitting a full course. Again, tree diagram visualization could be kind of helpful there.
175.
175 is a little bit big.
Hold up. 5 times 7 times 5. Oh, but you can only omit one course, right?
Yeah, I am at one. So it's not just adding one to all of these, because that's obviously going to include, like you probably just spotted, omitting all three at once, or anything in between.
So then is that just 120?
120 is a bit small. 120 was the answer to part B. Um, so again, sort of thinking about the tree diagram here, the branch that has omit then continues off to no longer have any further omits on it. Trickier. So it becomes a bit trickier to like draw that full tree diagram. That's a lot. Um, Omitting one course. The other way to think about this would be to start thinking about, okay, there are. I could either omit the entree, I could omit the main, I could omit the dessert, or omit nothing. I've now got four unique, distinct scenarios here, and so I just calculate each of those individually and then add up all the results.
Let's see.
That's yeah, the idea there. Now, yes, you could literally branch all those out as tree diagrams. Maybe not even label it. I don't know how hard it would be to. Yeah, sounds like there's a lot. Even if you just sort of, rather than draw each of the branches, you can kind of describe what's going on. Maybe even just labeling the omit ones, because that's the most important thing.
So, like, what we have to do is add up the probability of, like, add up the amount of meals if we omit no courses, and then omit either of the three.
Yeah, so you've now got four distinct scenarios that you're calculating back to back, and adding them all together.
Okay, I got 4, 5, 6 when I did that, but I think it's
Mm,
like way too big because
it
there's
is.
probably like courses that are in common in between all of them.
Yeah, so I'll show you what it looks like to do it. Okay, cool. So when you omit the entree, maybe the thing that wasn't being addressed here is when you like do the thing omit entree, that's a guaranteed choice now. So that's locked in as a selection of one. Same with omitting the main, same with omitting the dessert. That's now locked in as one option there. Everything else is then just what it was before. So if we've omitted the entree, you're going back to having the six mains and four desserts. So it's entree is guaranteed as omit, six then four. Now mains guaranteed as omit, four then four, because it was four entree, four dessert, so on and so forth. The omit none we've actually already calculated. That's the 96, which we did
At the very
um,
start.
all the way at the beginning.
Yeah.
I would hazard a guess. Yeah, what was different about what you did?
Well, I guess I didn't do the one where like you have one. I just like sort of added it
Hmm.
to the already pre-existing option. Like say there's 6 choices for me. I just did like 7.
Oh, yeah, yeah, yeah. So you said you kept this as 464, but then toggled like this to seven in one of them, this to five in one of them, this to five.
Yeah.
Okay, yeah, yeah, gotcha. Yeah, that's definitely one thing to remember when you're looking at a particular scenario. Um, Sometimes it adds choices, but oftentimes it'll also simplify things further.
Yeah.
This one
Cool.
here, we had a look at a few of these before, but it was a while ago. I reckon it's maybe unique enough for you to remember what was going on here.
Of choices of main course and 25 minutes M choices of dessert. This looks to me as a is this a tech? This is a tech-able question, right?
Yeah, well, it's oh, you can use
Yeah,
CAS for this one.
cool.
I guess
Um,
being extended response, it's always CAS, but they're a bit hit or miss with where they're labeling CAS or non-CAS. There's a few things weird about this one.
what are the possible values of M? Okay, so M has to be between 5 bracket root 17 plus 1 all over 2 and 20.
Possibly. Sounds good. The 20 sounds good. I don't really know about the root. I didn't write down the root.
Was there like a like did you round to decimal places?
I just when I was writing the answers, is it 12.8 as the bottom?
Yeah, 12.81, yeah.
Yeah, okay. Well, you've done the calculation right. So you've done the m multiplied by the half m multiplied by the 25 minus m because it's the multiplication principle,
Yeah.
and you've made that greater than 1,000, which is good. Obviously, not a great answer to use off rip, but it's the one that the CAS gives you. We just gotta process it a little bit.
So M has to be more than 13
That's a nice simplification. Yeah, it's gonna be
and
more than
less than 20.
I'd say more than or equal to 13, because when you're rounding up on the inequality,
Oh
it now
yeah,
becomes an inclusive.
right.
But that's still not the final answer, actually. It is getting
Really?
closer. Yeah. Yeah. That's usually where it stops. This one in particular has one further complication.
There's a negative answer as well, but I thought you would reject that.
Well, yeah. Yeah, you definitely want to reject a negative because M in this case. Well, what is
Has to
M?
be more than 30. It's a meal choices.
Is it?
Wait,
It's in a few different spots. What actually is M? And that's the complication. It's not actually just the choices of entree. It also impacts how many mains there are and how many desserts there are.
M has to be less than 25.
How'd you get up from 20 to 25?
No, no, I'm looking at the like 25 minus M, so that means like
Oh yeah, 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 sure. So yeah, if M got greater than 25, you now have negative choices for dessert. Yep, cool. Plug in some numbers in your inequality range. That's always a good default, and you'll pretty quickly realize something's a bit weird. Think about your experience as a diner. You're in here, and it's like, cool. If M is this, then I have this number of choices for entree, this for main, this for dessert. Does that make sense? Okay. How about this number?
no, I'm honestly not sure what the caveat is here.
All right. Well, did you plug in some numbers?
I plugged in 13 and
Okay. So you plugged in 13. That means how many entrees do we have?
That means we would have 13 on first.
How many mains?
6.5. I see.
Yep.
So now we have to do it has to be more than or equal to 14.
Okay. Keep plug it away. What if I chuck in 15 as M?
No, but if you put 15 in, then you're gonna have 15 on 2.
Yep. So greater than or equal to 14 still doesn't quite work because 15 is one of those numbers.
So then do you have to like say like M is an element of the like even numbers? I
Yeah.
mean, yeah,
Yeah.
even numbers.
Basically, you want it to be even is the main thing. Yeah, you could probably say something to the effect of, "Yep, this is my inequality range, and also even." It's also just small enough to where you could literally just list them all out.
Okay,
Yeah. So this one, like, this is probably the natural place to like. This is where most questions are going to stop because we typically when we're doing this stuff for like polynomial applications, it's stuff like length, and those can be decimal numbers. So we usually aren't super in tune with the fact that, oh, right, in this case, decimals don't actually work out all that well. Even within probability, right, when you've got like those massive arrays for discrete and you're finding out what M could be, even those, because they're probabilities rather than choices. Um, and so, yeah, it's one of those where you'll do it and then you'll remember, okay, cool. Got to make sure they're whole numbers as well as being positive, as well as being within this range of no decimals.
yeah, nice.
Yeah, as I said at the beginning, there's a lot of complications on that one. You'll probably get the exact same thing here in 2E, but I guess I'll work our way up for it. That is if you want to keep doing these, of course.
Yeah, we'll do them.
Wait, let's rock.
2A
2A.
720.
720 is correct, yeah.
Yeah, we'll do this little 2N
Basic
JB.
permutations.
8 out of 720.
Well, it's not a
Oh no,
probability.
wait, no, sorry, hold up. 16 on 720. And you gotta simplify it.
Well, it didn't ask for a probability.
Oh, would it be 16?
Not for part B, no. So
Okay.
two end chairs need to be occupied there. Um, you've got three people.
So I'm thinking that okay, so for the first person, they'll have two choices. Let's just say we want to occupy the chair with the two people
Yep.
with this like with the first people. So the first person would have two choices,
Mm-hmm.
and the second person would only have one choice, and then
Mm.
the last person has eight choices because they can sit wherever they want.
Mm. Yeah, okay. Hang on. Have I written my answer wrong then? What's going on here? Hang on. How many of these will the two end chairs be occupied? Oh no, because there's three people. Yeah, the initial premise you had was a bit off. You got three choices for that first spot, then two choices for the next spot, not two and then one. It's you want to go backwards whenever the number of positions is smaller than the number of sorry, other way around. Whenever the number of things you have is smaller than the number of positions, you need to in your mind flip that because it doesn't really work out too well.
So you need to say like, oh, the first person, the
Yeah, so
first
there's
chair can be occupied by three people, and then
yeah. So it's
two and eight.
three people could take that first spot, two people could take that second spot, and then the last person now has eight possible spots. So sometimes in these, again, it's you got to be a bit flexible with it. the thing that tends to come up a couple of times is, hey, we want to make sure that whenever we're doing a thing, the number of positions is always smaller than the number of things you have for those positions. And that might very well just be that you have to literally do both, like reverse that in the exact same uh, multiplication, which is really sort of strange to think about, but it does get you the answer. These are nasty questions, but
Yeah.
yeah, like if you think about it, just as like, okay, if I have three, then two. Um, the next number, it's people. Yeah, you would then think the next number would be one here, but I think it's good to start framing things as this is what I'm doing to address the restriction, and then this is what I'm doing to backfill. We did the three and the two to address the restriction, and then the last bit was just backfilling the rest of the scenario. So breaking it down into effectively two scenarios. Step one, I'm going to fill in these seats. Step two, I'm now going to say, cool, I got one person left, 8 spots for them. That's 8 remaining. So almost like treating it like with the team examples, 8 boys, 3 girls, whatever that is, you're doing that in a sequence. Except in this case, it's here's the restriction, here's everything else that we got to do afterwards. Maybe that helps. Half though. Is that fair
Okay.
enough?
Yeah. Hopefully I can get 2C right.
Yeah. I mean, this one will be a bit easier to
Is it
see.
336?
Yeah, 336. That one's got not too much there. You just knock them off total.
What is the probability that the two end chairs will be empty?
That'll also be quite chill.
Um, Let me simplify.
Mhm.
7 on 15.
7 on 15. Yeah, taking that 336 that we just calculated, 720 that we calculated at the very beginning. Yeah, cool. And now part E, you get to practice this again. Although there's actually a little bit less complications in it, but still
Ooh,
should be considered.
okay. What I want to do is n times n minus 1
Mm-hmm.
times n minus 2,
Yep.
and then see where it's 1,000 and where it's 1,500.
Yeah.
Okay.
Um, just a pro tip on this one: the CAS can actually do double-sided inequalities.
Oh,
So you,
really?
you can actually, yeah. I saw this one, and this is the first time I figured that out. Actually, I was like, huh, I wonder if the CAS can sort this out. And lo and behold, if you plug in literally that, you do you do in fact get it, which is
Damn,
kind of funny that it can handle that, but it doesn't like doing the factorial stuff. It'll kind of complain about it if you give it factorials.
yeah, some CAS abuse right there.
Has abuse, nice. Yeah, but yeah, that'll
Holy.
mm,
Um, okay. I thought my CAS was about to crash, but it just looked
ha,
loaded for a really long time.
yeah, yeah, it'll do that.
Okay. Surely it'll give me a nice answer. Okay. Is it between, okay, it's not really specified in decimal places, but I'm not going to give it an exact form.
Hmm.
Uh, 11.03 and 12.48.
Those are the numbers that CAS gives. Yep.
Yeah. Were they correct?
Yeah, the numbers are the CAS are giving you the correct numbers, but it's not your final answer. What is n?
N is more than or equal to 11.03 and less than or equal to 12.48.
Yeah, but what does n stand for in the scenario?
All right. The amount of chairs. So
Yep.
then n is more than or equal to 12 and less than or equal to 13.
Okay, so here's another. Actually, test those.
Oh, it's just 12 or 13.
Yeah, test those. So you can actually plug in n is 12 into your n minus 1, n minus 2. Same thing with the n equals 13. And this will, I'll see what kind of conclusion you derive from that.
Hey, 13 doesn't work. So
Yeah, it doesn't work.
it's only, wait, I'll just try. It's only 12.
Only 12, yeah.
No,
So,
this is a question, bro.
say again?
It's me. Like the end part, like getting to the final product.
Yeah, yeah. Which is why we do these, because um, before I give away what the actual learning there is, why do you think 13 didn't work?
Because we were rounding up. So it
Yeah,
might have gone outside of it, because it went outside the bounds when we were rounding up.
yeah. So what's wrong about rounding up?
It
Um,
goes outside of the actual like end value.
yeah, yeah. So even though the decimal, I mean, in this case, decimal was zero point 0.4, so it should have rounded down anyway. But even if you had like 12.99 here, that's still not good enough. Got to go down to 12. And so the rule when you have these double-sided inequalities is you round inwards. So left rounds up and right rounds down. And because they both round to the same number, well, then you just give the 12. This one was easy enough for you to plug in some stuff, so I was happy to let you do that. Other times you're going to get, even the previous one wasn't that bad to plug in numbers, but that you can imagine other circumstances where you have a lot of different things. And so taking home these lessons is going to be helpful for these sorts of things. I don't believe these get much more difficult. I can throw in some conditional probability stuff. They do teams of people. This is also a kind of teams of people thing. Flat batteries and charged batteries. Boys, girls. You know, two unique separate teams. Maybe we'll do one of these if you're happy for it.
I mean, if there's some content to go through, I don't mind doing these my own time because
Yeah.
I just finished my last exam today, so I'm at home for the next 3 days.
Okay. Brilliant. Awesome. All right. So you'll definitely want to go through all of those, and I would even say D as well. D is also a bit of a mix mash of all sorts of things, and well, as you can see, because I was referring to them, I do actually have work solutions to these things um, in the relevant module. So if you do get stuck with them, just have a look at whatever bullshit I was spouting, and if it makes sense, then happy. If not, give me a text and I'll fix it.
Okay.
Cool. So that's that. So if that takes us through counting methods, the next thing would be some discrete fundamentals. We've kind of already done this, but at least like we've looked at similar things today. With discrete, so this is probabilities whenever you have a specific number of countable things. Basically, you don't want to have any decimals in here. Um, you have basically everything we're doing in counting methods. All of those were discrete scenarios. One of the things we look at in the year 12 discrete stuff are these, in fact, even year 11 does this, probability distribution tables. The way it starts working here is they actually label the scenario as like capital X, capital Y, capital whatever, and that is there to determine what the probability scenario is that we are discussing. So there's no actual examples here. We'll do this one instead. So we got a jar of 4 white, 6 black. Capital X, the probability distribution is around white balls. And so capital X will be the discrete random variable. That's the keyword for it. Discrete random variable is the number of white balls drawn. So whatever that capital letter is, basically informs what's actually being looked at within the scenario. as for how the rest of the table works, little x are all the possible outcomes of capital X, the scenario itself. So in this case, it's saying that our discrete random variable can be anywhere between 0 and 3 as integer values. So what that might look like in a real thing would be we're drawing 3 balls from this jar, and so the number of white balls that we draw could be anywhere from 0 to 3. Right, whether we draw none, 1, 2, or 3 white balls back to back. Oh, sorry, not even back to back, actually. This is just how many we left with at the end of the experiment. And then lastly, this row here is all the probabilities of those things occurring, which you can calculate in all sorts of different ways. We'll look at that. And in fact, yeah, all of the counting method stuff works for this. There's also some other stuff that we do that's a bit more fundamental. These are to be referred to and considered pretty much always whenever you're doing discrete probability stuff. These are also just broad probability rules that apply literally to all probability, but they're exceptionally useful also in discrete. All probabilities be between 0 and 1. They must all add up to 1, and the reason why is because this is a complete description of the entire scenario, so they should all add up to 1. And complement probabilities are often coming in handy to help reduce the amount of effort it takes to fill out a table like this. This sort of stuff has nice applications in when you're solving continuous stuff, when you're doing like your integral boundaries, specifically this one here. What else comes into play? Normal distribution. Nah. Normal distribution uses a lot of this actually. Complements. Anyway. So how we fill out a table, it's completely dependent on the scenario. There's no one way to do it. Because it is discrete, all the counting method stuff works perfectly fine for it, although it is kind of heavyweight. You don't really want to do it if you don't have to. You probably just almost always are using a multiplication principle of some sort. And you don't necessarily have to do it based off of the number of combinations. You can actually do it, after division, after it's become a probability. Like for instance, in this scenario, there's 4 white, 6 black, and they are drawn with replacement, which means we're basically picking a ball, noting the color, chucking it back in, giving it a bit of a shuffle, and then picking out another one. And so, because you're doing that in sequence 3 times, you're multiplying the probabilities back to back. Yes, you could calculate combinations for each stage and then divide by total, but that's a lot more effort. Especially when it's a with replacement scenario, because you can calculate your baseline probabilities of black and white, and then just smack them together. X equals 0 means 3 blacks, because again, we've got to make sure that we are keeping track of what's actually going in the table. 0 means 3 blacks, not 3 whites. That'll matter if there's not a 50-50. So multiply 3 blacks together, you get that. For anything in the middle, a lot of the times it'll be kind of like how you do arrangements, where the ways in which you could create those things matters. And the reason why is sort of back to what a discrete table actually is, which is it's a bit higher level in the sense that it only looks at the outcome at the very end of the experiment, which is you've drawn your 3 balls, how many of them were white? I don't care how we got there. The probabilities kind of are, you need to know that to calculate the probabilities, but this is kind of like a snapshot at the very end, which is cool. We had 2 at the end, let's say, and there was a probability of that to make that happen. So that sort of information is lost. You have to dig into that to actually figure out what these are going to be. Depending on the scenario, if it's with replacement, these you can just replace with a multiply by 3, since all you're doing is changing the order in which multiplication is happening. If it's a without replacement, then all of these numbers are decrementing a little bit. Like for instance, if you pick a black ball, it's going to go from 6 out of 10 to now 5 out of 9, because one of the blacks has disappeared, but also one of the total has disappeared. Um, we might see an example of that somewhere. X equals 2, same shit, but now you got two whites. And yeah, x equals 3 again. We've seen that before. If you want to do a quick sanity check, just make sure everything adds up to 1, and you can be very certain that you've done your table right in that case. These are very easy to use if you want to find a probability over a given range of values. So x greater than or equal to 2, you literally just go, yep, x equals 2, x equals 3, that's all of those combined. You just add them up. Plain and simple. Sometimes you can't. You got 1, 2, and 3 here. You don't know any of them, but you do know the other stuff. That's all your complement probabilities come into play. And this is like the very typical example that shows up in like a multi or maybe at the very end of an extended response. Yeah, or a tech free that's particularly vicious. You're basically making use of most of the basics of probability, which is, hey, we want to make sure we have no negative probabilities. We want to make sure they're between 0 and 1. And finally, we want to make sure that everything adds up to 1. Actually, yeah, that's actually a perfect example of using literally all three of these things. Oh no, no compliments. Sad. Anyway, how do we do it? We start by adding everything up to 1. Simplify. Look at that, we got a quadratic. Solve that however you like. This one could have been factorized. But as soon as there's a coefficient here, I pretty much just say stuff it. I'm not going to be bothered doing my so what is it? You do a grouping method for this, which I've actually started to like a bit more than
Oh, did
doing.
you? Is it the one that I showed you a few
Yeah,
months?
yeah. The grouping thing.
Yeah, I
It's
mean, I guess quadratic formula is like probably going to be more applicable because you're not always going to get a perfect quadratic.
yeah. So like you can play the grouping stuff where you can go, yeah, it's the 5 and 1 to get into 4. Um, and then yeah, splitting that up into two of these coefficients and group.
Yeah,
Obviously, it doesn't always work, so that's why I'll pretty much just default to quadratic formula anyway. Um, yeah, but it's a lot closer to being better. Like it's definitely better than the cross product thing.
yeah. I could never get my head around that. Like it was just way too
Yeah.
hard. I was basically like, trying to like
Uh,
memorize quadratics until my teacher told me that. So
okay, interesting. I actually, because you mentioned it as well. I also saw it with who was it? I think it was like either one of my year 8s or year 9s, and we were just going through basic chapter stuff, and it was a grouping method thing, and I noticed a similarity there. I was like, huh, all we're ever doing here is grouping. That's interesting. Yeah, factorized by grouping. But anyway, you'll get your two solutions. Um, it's never really mattered, but I feel compelled to say it anyway. P is not actually a probability in this scenario. It's a coefficient of a probability. And so I can imagine that maybe some very strange question could allow a negative P.
yeah, because there's
Um,
squares in here, so
yeah, some squares in there make it happen. Oh, whoops. Where did I go? Yeah, some squares in there can flip that to being positive. Maybe even these numbers are negative, and double negative flips back to positive. So it's not out of the realm of possibility, but I mean, I've never seen it. I just feel compelled to give the warning anyway because it might happen. That, and at least it just sort of deepens your understanding of the scenario. But yeah, just basic common sense. You'll see this fraction, you'll see this whole number. It's probably going to be the fraction.
yeah.
And lastly, conditional. So conditional probability.
Just cut off anything that's larger than three. I mean, sorry, cut off like three, and then look at one out of that thing.
Yeah, can you? Can you just look at from 0 to 2? It's a bit hard for these because, yes, you restrict the sample size, but you don't actually know what your new total is. Oh, do you? Hang on.
You just add the
Yeah,
thing.
but it's still there because this becomes your new total. which you need, like, yes, that's your new sample size that you're working off of. So it's still your denominator. Like, I guess I'm just saying, like, I don't think there's really a way for you to cut this out entirely and just say, oh yeah, I'm just looking at this bit of the graph. Because it is
Okay.
pure probabilities rather than what you can do with the when conditional probability was introduced to you, you were given it in terms of the raw numbers, and those you could definitely dick around with a lot easier because you could very quickly see. I'll just pull it up. You could very quickly like have a look at this column and be like, oh yeah, I just want this one. It totals to this. Easy. Forget everything else. Because you don't actually have the raw numbers here. You just have the probabilities. It's kind of hard to do that.
Yeah, right. It's
Yeah. But yeah, still a basic idea. The basic idea is still the same, which is, yep, we're looking at this particular group, so that's my new denominator, and then whatever's in here is my new numerator.
yeah,
And that brings us to time. We're a little bit over.
yeah,
Cool. So as far as the next steps for you, probably the main thing there that's toughest would be get through your 10D, get through your chapter 10 review, and maybe even the Jacaranda version of those as well, if you're still feeling like it's a bit iffy. I don't have solutions for Jacaranda, but I'm hoping that if you get through Chapter 10D and Chapter 10 review, you've probably got enough to work off of to solve the Jacaranda ones yourself.
yeah. Cool. Thanks.
Easy. I'll leave you to it.
Yep, see ya.